discuss the pH scale. So Søren Sørensen, a biochemist at Carlsberg Brewery in Copenhagen, Denmark, proposed an alternative method of specifying the acidity of a solution, and this is called the pH, or the power of hydrogen ion. So we have a formula for our pH, and this is pH is equal to negative log of H plus, or pH is equal to negative log of H3O plus. Take note that H plus is just a short term of our H3O plus, or our hydronium ion. And take note that for a neutral solution, there is a 1.0 times 10 to the minus 7 concentration of our hydronium ions. So, at neutral solution, we have a negative log of 1.0 times 10 to the minus 7. So, we have a pH equal to 7 if the solution is neutral. If the solution is basic, the pH is greater than 7. Well, when the solution is acidic, the pH is less than 7. Now, again, pH is the short term for the potential of hydrogen, and this is a symbol and denotes the relative concentration of hydrogen ions in solution. The pH values extend from 0 to 14. The lower the value, the higher the acidity, or the more hydrogen ions in the solution contains, or the solution contains. And take note that water at 25 degrees Celsius has a concentration of H plus ion of 1.0 times 10 to the minus 7. So the pH therefore of our water is 7. So the number of hydrogen ions present in a solution is a measure of acidity of a solution. So all acids do not ionize completely when dissolved in water. That is, all the molecules of acid do not ionize and exist in the solution as electrically charged particles. The hydrogen ion concentration is a measure, therefore, of the amount dissociated acid rather than the amount of acid present. So again, the measure of acidity is based upon the concentration of our dissociated H plus ion or hydronium ion, and not the amount of the acid present. So, take note that the pH decreases as our hydronium concentration increases. So, therefore, remember the ionization constant of our water, or the water ionization constant, that is equal to negative log of 1.0 times 10 to the minus 14. And if you have this hydronium ion concentration that is greater than 1.0 times 10 to the minus 7, and you have less than 1.0 times 10 to the minus 7 concentration of your hydroxide ions, therefore the pH is less than 7. So, the solution is considered as acidic. But when the concentration of our hydronium ions and our OH ions in the solution is equal to 1.0 times 10 to the minus 7, therefore the pH is equal to 7. So, the solution is neutral. When the concentration of H plus ion is less than 1.0 times 10 to the minus 7, while the OH minus concentration is greater than 1.0 times 10 to the minus 7. So, this means that we have a higher amount of OH minus in the solution. Therefore, our pH is greater than 7, or the solution is basic. Now, you have to remember all of this in this table so that it will guide you to predict whether the solution is acidic, neutral, and basic. Let's try solving this sample exercise in number 1, in which a sample of lemon juice has a concentration of hydronium ions, or H plus, equal to 3.8 times 10 to the minus 14 molar. So the question is, what is its pH? So we are going to solve the pH. Remember that the formula of our pH is equal to negative log of H plus. And take note that the H plus concentration here is given. So the answer therefore here is pH is equal to negative log of 3.8 times 10 to the minus 4 molar of H plus. So that is negative log of 3.8 exponent minus 4 that is equal to 3.42 or 3.4. The pH is 3.4. So take note, when the pH is less than 7, the solution type is acidic. Therefore, the solution type here in number 1 is acidic. Acidic since pH is less than 7. Now, let's go to sample exercise number 2. A common available window cleaning solution has a H plus concentration of 5.3 times 10 minus 9 molar. So, what is its pH? Take note again, we have the same formula for pH, that is negative log of H plus. Therefore, we can input directly the concentration of our H plus solution from a window cleaning solution, which is equal to 5.3 times 10 to the minus 9. So that is just pH is equal to negative log of the H plus concentration, which is 5.3 times 10 minus 9. So when we calculate, that is negative log 5.3 exponent minus 9. That is equal to 8.3. So, take note that our pH is greater than 7 since it is equal to 8.3. Now, when we detect the solution type, whether it is acidic, neutral, or basic, since the pH is greater than 7, therefore, the solution is basic. The solution type is basic since pH is greater than 7. Now, let us continue to solve the problem, which is a sample of freshly prepared apple juice has a pH of 3.76. So now, we have to calculate its H plus concentration. Again, do not forget that the formula for our pH is that is equal to pH is equal to negative log of H plus. So here, what is asked is the H plus concentration. So in order to get the H plus concentration, that is just equal to the inverse of log to the minus of pH. This is log to the base 10. So the inverse of log to the base 10 minus pH. Then this is equal to 10 to the minus 3.76. So if we are going to get the answer, that is equal to 1.74 times 10 minus 4. So that is the concentration of our H plus. That is equal to 1.74 times 10 minus 4 molar. So the concentration here is in terms of molarity or mole per liter. Mole per liter. So now let's go to number 2. A solution formed by dissolving an antacid tablet has a pH of 9.18. So we have to calculate its H plus. So we have the same approach since the H plus is sought here. So that is just H plus concentration. That is equal to 10 to the minus pH. So that is equal to the inverse of log, which is 10 to the base 10, minus 9.18. 10 to the minus 9.18. I'm sorry. 9.18. So if we are going to get the answer, it is inverse of log to the minus 9.18. That is equal to 6.61 times 10 to the minus 10. 6.61 times 10 to the minus 10. 6.61 times 10 to the minus 10. That is in terms of molarity or mole per liter. It's hard for me to write the mole. Can't write the mole per liter. Okay? So that's it. Now, there are other P scales. So, if we have pH, there is also a pOH. In order to get the pOH, that is just equal to the log of our hydroxide concentration or negative log of our hydroxide concentration. And if we are going to get the negative log of our um, ionization constant for our water, this is equal to our pKw. Then remember, our ionization constant for water is equal to the concentration of your hydronium ions times the concentration of your hydroxide ions. So if we are going to get this pKw, which is equal to negative log of Kw, our pH, which is equal to negative log H plus, and plus pOH, since this is equal to negative log of OH minus. So take note that we have a Kw, which is equal to negative log of 1.0 times 10 to the minus 14. So from this, therefore, the pKw is equal to negative log of 1.0 times 10 to the minus 14. pKw is equal to 14. Therefore, our pKw here is 14. Therefore, pH plus pOH is equal to 14. Take note that Ka represents the acid dissociation constant, while your Kb represents the base dissociation constant. When it refers to pKa, that means that is equal to negative log of Ka. When it refers to pKb, that means that it refers to the negative log of Kb. So do not forget this expression, the pH plus pOH is equal to 14, the pKa, and our pKb. And then, for measuring the pH, there can be a qualitative method and a quantitative method. For the qualitative method, we can use the litmus paper, the red and blue litmus paper. We have discussed how to use it at the start of this chapter of our discussion. And for a second way to measure the pH, we can use a pH meter, and this method is quick and accurate, and it will give us the quantitative data for our pH of the solution being measured. So now, let's talk about strong acids and bases. Remember, when you say strong acids and bases, they are considered as strong electrolytes. So they are 100% ionized in solution and exist in a K solution as entirely ions. So these are examples of our strong acids, and these are examples of our strong bases. Now, HNO3 or nitric acid is considered as a strong acid. So they exist as ions in the solution. It will dissociate into H plus or hydronium ion later on when it combines with water, and the NO3 minus na ion. So in a aqueous solution of a strong acid, the acid is normally the only significant source of ions. That is, H plus is equal always to acid. Now, let's go to strong bases. So here we know that the solution is base when we have the increasing concentration of your hydroxide. Take note that you know that the solution is acidic when there is an increased concentration in your H plus ion or hydronium ion. You know that the solution is base when there is an increased concentration in OH minus or hydroxide ion. So now, we have a sample exercise here. What is the pH of a 0.011 molar of calcium hydroxide? Take note that CaOH2 from the hydroxide itself, from this formula, you know already that this substance is basic. So the given molarity here, therefore, is this molarity corresponds to the OH minus or hydroxide concentration of this calcium hydroxide. So to get the pH, remember that this one corresponds to OH minus concentration. So first, if we are going to use this, we are getting the pOH. So when we say pOH, that is just negative log of our OH minus. So that is negative log of our 0.011 molar na calcium hydroxide. If we are going to get the negative log of 0.011, the answer is 1.9586. Let us not, what do you call this? Let us not round off the number since this is not yet the final answer. 1.9586. Again, this is a pOH, so there is no unit. Now, when we get the pH, remember that pH plus pOH is equal to pKw, which is equal to 14. So that is just 14, or pH plus pOH. Remember that pH plus pOH is equal to 14. You have a value for your pOH now, which is this 1.9586. Now, in order to get the pH of the solution, that is just equal to 14 minus the value of your pOH, which is equal to 1.9586. That is then equal to 14 minus 1.9586. The answer for your pH is 12.041. 12.04. That is the value of our pH, or 12.041. That is the pH value of this calcium hydroxide solution. So take note that our pH tells that the solution is basic since the pH is greater than 7. That is equal to 12.041. Now, another example is what is the concentration of a solution of KOH, or potassium hydroxide, which has a pH equal to 11.89. So take note, the pH of the solution is 11.89. And what is asked is the OH minus concentration, or the solution of this potassium hydroxide. So how to get the OH minus concentration? In this case, we have to make use of our pH plus pOH. pH plus pOH is equal to 14. Now, our pH is equal to 11.89. So that is just 11.89 plus pOH is equal to 14. So in order to get the pOH, that is equal to 14 minus 11.89. So that is then equal to 14 minus 11.89. So the pH, therefore, the pOH is equal to 2.11. Take note that the formula for your pOH here is pOH is equal to negative log of OH minus concentration. What is asked is the concentration of potassium hydroxide, which corresponds to your hydroxide in this solution. So this then will then be manipulated to OH minus. In order to get the concentration of our hydroxide, we have to get the inverse of log to the base 10 minus our pOH value, or that is 10 to the minus 2.11. Therefore, the answer here is the concentration of your OH minus is the OH minus concentration is equal to 10 to the minus 2.11 inverse of log. That is equal to 7.76 times 10 to the minus 3. 7.76 times 10 to the minus 3 molar, or moles per liter. Take note to have a label so that we are sure what is that number pertains to. Okay. So now, similarly, for the extreme dilute solutions of bases, we can still use the this formula, the pH, pOH, and the pKw. So the question is, what is the pH of a sodium hydroxide solution with a concentration of 8.0 times 10 to the minus 8? So sodium hydroxide is a strong base. So what is the pH of the solution? So take note that this is the concentration of your sodium hydroxide. Therefore, this pertains to the OH minus. So if we are going to use this, we are getting the pOH, negative log of OH, that is equal to negative log of 8.0 times 10 to the minus 18. So negative log of 8.0 exponent minus 18, that is equal to 7. I think we're wrong. That is, sorry, negative log of 8.0 times 10 to the minus 8 lang, not minus 18. So that is minus 8. So negative log 8.0 exponent to the minus 8. So we are getting a pOH which is equal to 7.0969. So again, we should not round off numbers yet, since we haven't arrived to the final numbers of final digits of what is being asked. Now, the question here is the pH, not the pOH. So then we can we can use the pKw, which is equal to 14, is equal to pH plus pOH. So that is just equal to pH plus pOH is equal to 14. So our pH therefore is equal to 14, which is minus 7.0969. So the pH of this solution is equal to 6.90 or 6.9. The pH is equal to 6.9. So the pH of the solution is equal to 6.9. Take note, when it is a pH, it doesn't have unit. But when it is a concentration, it should have a unit, which is equal to molarity or moles per liter. So we already have answers for this problem. And the next problem is an aqueous solution that contains 0.10 molar sodium hydroxide. This solution can be acid, base, or neutral, so we have to prove. Take note that sodium hydroxide is a strong base, apart from this one is a base, and 0.10 molar sodium hydroxide pertains to the hydroxide concentration. So if we are going to get the pOH, pOH is equal to negative log of that 0.10 molar. So that is equal to negative log of 0.10. So the pOH is equal to 1. Take note that pH plus pOH is equal to 14. When we get the pH, that is just 14 minus pOH, or that is equal to pH is equal to 14 minus 1. Therefore, the pH is equal to 13. Take note, when the pH is greater than 7, the solution is basic. So, therefore, the solution is basic since the the pH is greater than 7. Okay, so that is a proof that the solution is basic. So another problem is a neutralization between the ammonium hydroxide and hydrobromic acid will form what from these choices? Take note that this ammonium hydroxide is a base here. NH4OH is our base. So when we say base, this is the Bronsted-Lowry base, we said that this is a proton acceptor, H plus acceptor. And your hydrobromic acid here, or HBr, is your Bronsted-Lowry acid. Or this is the, what we call the proton donor. So this is the proton donor. Now, I'm sorry, I can't write it properly. So that is the proton donor. So what are their products? Take note that this is a strong base and this is a strong acid. So they will completely be converted to products. So in this case, this one will accept the protons, the NH4OH. So the HBr will donate its proton. So when acid-base reacts, take note that they cancel each other's property, so they will produce water. So the OH here will get, from its electrons, it will get the proton from the hydrobromic acid, and this hydrobromic acid will donate its proton. So it will lead to the formation of water plus the NH4 plus ion and our bromine ion, or NH4Br. Okay? So this is the products. These are the products between the neutralization of our ammonium hydroxide and HBr. So the answer here is letter A. Just remember that when a base and acid reacts, it will undergo a neutralization reaction producing water. Okay. Now, nitric acid is a strong acid. This means that its pH is less than 7. Apart from that, when you have a strong acid, it will dissociate completely in the solution. Sorry. It will dissociate. It will not erase. Can't be erased. It will dissociate in a solution. Now, what is the pH of an aqueous solution in which H plus is 0.025 molar? So simple, that is just pH is equal to negative log of H plus. We have H plus concentration here. So that is equal to pH is equal to negative log of 0.0025 molar. So that if we are going to get it, negative log of 0.0025 molar, that is equal to 2.60. So the solution therefore is acidic since the pH is less than 7. What is the concentration of hydronium ion at 25 degrees Celsius with a pH of 4.282? So remember again, the formula of pH is equal to negative log of H plus. In order to get the concentration of our hydronium ion or H plus ion, we have just to get the inverse of log to the minus pH. So that is just 10 to the minus 4.282. Okay, or inverse of log to the minus 4.282. So that is equal to 5.224 times 10 to the minus 5 molars or mole per liter. Now, what is the pH of an aqueous solution that contains this concentration of H+? So you just use pH is equal to negative log H+. So that is equal to negative log of 3.98 times 10 to the minus 9. So negative log of 3.98 exponent minus 9. That is equal to 8.40. The pH is 8.40. So since the pH is greater than 7, we can conclude that the solution is a base. Now, for the reaction between HI and water, tell what is the conjugate acid and the base. Remember that your water is an amphoteric substance or an amphiprotic substance. So it can act as either acid or a base in the solution depending on its partner. This time, we have HI. So HI is a strong acid and it reacts with our water. So since this is the acid here and our water is amphoteric or amphiprotic, so this is the base. So it will dissociate completely into the product. So our arrow is straightforward to the product. Now, when you are an acid, you are said to be the proton donor. So it loses its H plus since the H iodinates it to water. So what is left is our iodine, or we have here the I minus. Now, in the case of our water, we just have to add the additional proton from the HI or from our acid. So it will form H3O plus. So now, our acid here forms its conjugate base, which is the iodine minus. Well, our H3O plus or hydronium here is the conjugate acid or Ca, conjugate acid of our base, which is the water. Okay? So now, let's go to the weak acid. So, if we are going to compare it with strong acids, if strong acids completely ionized in a solution, weak acids are only partially ionized in aqueous solution such that dissolved molecules exist in equilibrium with their ions in solution. So take note that the extent of ionization of a weak acid is expressed by the equilibrium constant for the ionization reaction. So example, we have a general weak acid which is HX that reacts with water to form hydronium ion, and this it's what they call this, it's conjugate base. Now take note that when we have a ion dissociation constant or dissociation constant of an acid, we have it as a Ka. So the equilibrium constant is just equal to products over reactants. Our products here is the H3O plus and its conjugate base of your acid. So that is equal that is over the reactants, which is equal to Hx. So take note that the Ka stands for our acid dissociation constant, and the magnitude of our acid dissociation constant indicates the tendency of the hydrogen atom to ionize. Therefore, the larger the value of Ka, the stronger the acid. This is because when you have a higher value of Ka, you have a higher value of the H3O plus concentration. Take note that our H3O plus concentration and our Ka is directly proportional to each other. So when there is a high amount of H3O plus, therefore the acid is strong. Okay? So consequently, you will be having a higher amount of Ka value. So we have an established values of Ka for different weak acids at 25 degrees Celsius. And here is the table. Now, this is the equilibria involving a weak acid. So first we have to how to calculate the pH from the Ka. So example, we have to consider that there is a 1 molar of acetic acid. Our acetic acid here is a weak acid. So we have to calculate the equilibrium constant of the acetic acid, which is HOAC, and the H3O plus and the acetate ion, or the OAAC, and the pH. So this is the general equation for the reaction. We have acetic acid that reacts with water to form H3O plus, and our acetate ion, which is the conjugate base of our weak acid. So if we are going to get the acid dissociation constant, or our Ka, remember that is just products over reactants. So our products here are the H3O plus and our conjugate base, which is the acetate ion, so over the reactant, which is the acetic acid. So the constant Ka for acetic acid is equal to 1.8 times 10 to the minus 5. Next, when you have defined this, we have to define the equilibrium concentration using the ICA table. When we say ICA table, we have to account the initial, change, and equilibrium concentrations of our reactants and product. Take note that we have 1 molar of acetic acid at starting point, and at starting point, the ions, this acetic acid does not dissociate still in the solution. So upon change, so it dissociates already in the solution. So there is a value now for your H3O plus and a value for the conjugate base of our acetic acid, which is the acetate. So we have to add that. We have to represent that by a letter X. We have to add that in the right portion, since that those are in the product portion. And we have to deduct this value from the 1 molar starting point of our acetic acid. So when we get the equilibrium, that is just 1 minus X, which is the lost H plus during the change, when the acetic acid reacts with your water and forms the equilibrium between the H3O plus and the acetate ion. Now, our H3O plus here is represented by the X variable, the same with our acetate ion. It is represented by the X variable. Take note that the concentration of H3O plus and acetate ion is just 1:1. So what is the concentration of your H3O plus is just the same as the concentration of your acetate ion. So we can represent both with X. So in order to get the equation, that is just X times X, that is equal to X squared. And remember that our acetic acid at equilibrium, that is equal to 1.00 minus X. So we have to place that in the denominator. And take note, if we are going to disregard this expression for the Ka, this one, and if we are going to, okay, let's write na lang. Okay, let's write it na lang. If we are going to have a Ka, which is equal to, take note that your Ka is equal to 1.8 times 10 to the minus 5, that is equal to X squared over 1.00 minus X. So if we are going to multiply this 1.8 times 10 to the minus 5 times 1.00 minus X, then we have X squared at the right. And if we are going to continue this will be solved using a quadratic formula. So we can make an approximation if X is very small. So when X here is very small, meaning that amount is very negligible. So if X is 10 to the minus 6, 10 to the minus 7, 10 to the minus 8, 10 to the minus 9, and so on and so forth, meaning that is just a very negligible amount. So we can neglect this minus X here and continue to calculate with this X squared over the initial concentration of your weak acid. So again, we can ignore the minus X in the denominator if the acid dissociates less than 5%. So now, first, assume that X is very small because the Ka is small. So we can then, simplify the expression to Ka, which is equal to 1.8 times 10 to the minus 5 is equal to x squared over 1, since we already neglect this value, since again, this is a very small value. Now, we can easily solve this approximate expression. So again, these are just some notes in calculating Ka from pH. The weak acids are simply equilibrium calculations. The pH is used to calculate the equilibrium concentration of H plus. And first, what we are going to do is to write the balance equation clearly, showing the equilibrium. Write the equilibrium expression and use an ICE chart to find the H plus from the pH, then find the value of your Ka. And take note that there is what we call the degree of ionization. The degree of ionization of a weak acid is the fraction of the electrolyte initially present that ionizes. So we can get this expression or the percentage ionization as percentage alpha, which is equal to the quantity ionized at equilibrium, or the H plus at equilibrium, H plus concentration at equilibrium, over the concentration of your acid at the starting point times 100. So with regards to the relationship of our degree of ionization and acid dissociation constant, the percentage ionization is directly related to our acid dissociation constant. So the smaller the value of the acid dissociation constant, the lesser the degree of ionization. The lesser the degree of ionization, meaning the weaker is the acid. So for this problem, we have at 25 degrees Celsius, we have a 0.1 solution acetic acid and it's 1.34% ionized. So now the question is, what is the ionization constant or Ka for acetic acid? So we are given with a 1.34% ionized, and this is the formula for our ionization. So meaning that is just 1.34%, that is just equal to 1.34% is equal to the concentration of your H plus over the concentration of your acetic acid at starting point, CH3COOH. Take note that the concentration of our acetic at starting point is 0.1 molar. So we can delete this and change and plug in the 0.1 molar starting point concentration of our acetic acid. From here, we can calculate the H plus concentration, which is equal to 1.34 times 0.100 molar. I mean, this is, there is still times 100 here. So we cannot multiply, we cannot solve that directly. So we have to divide this 1.34 with 100 and multiply the whole term with 0.1, which is from our acetic acid, or 0.100, or the initial concentration of your acetic acid, so that we could get the expression, the H plus concentration. So that would be H plus is equal to H plus is equal to 1.34 divided by 100 times 0.100 molar. So the concentration of our H plus therefore is 1.34 divided by 100 times 0.1. That is 1.34 times 10 to the minus 3. Okay. So concentration of your H plus is equal to 1.34 times 10 to the minus 3 molar. Sorry. Then we have to write the concentration of your H plus is equal to 1.34 times 10 to the minus 3 molar, or moles per liter. So again, 1.34 divided by 100 times 0.1, 1.34 times 10 to the minus 3. Now we have a concentration of our H+. We have to write the equation of your acetic acid. CH3COOH, that reacts with your water, or that ionizes in your water, since that is a weak acid. So there is a equilibrium between the products and reactants. So this forms CH3COO minus, or its conjugate base, plus H3O plus. At initial point, we have a 0.100 molar concentration of our acetic acid, and we have 0 concentrations here. At change, we have a value of 1.34 times 10 minus 3 molar for your H3O plus. Since this is just 1:1, so with this acetate ion, so meaning they just have the same amount. So we have to place plus 1.34 times 10 minus 3 molar here, plus 1.34 times 10 to the minus 3 molar here. Well, here we have to subtract the ions that dissociates into the product side. 1.34 times 10 minus 3. So at equilibrium, that is 0.1 minus 1.34 times 10 minus 3. And we have plus 1.34 times 10 minus 3. Plus 1.34 times 10 minus 3. So if we are going to get the Ka, we are going to use the equilibrium data of our of each of our compounds here in the chemical equation. Okay, so we have to have the products over reactants. Our products are CH3COO minus times H3O plus concentration in molarity over the concentration of our acetic acid, CH3COOH. So in order to get the Ka, that is just 1.34 times 10 minus 3, which is the concentration of our CH3CO minus, times 1.34 times 10 minus 3 over, take note that the value of our H plus is big. So, I know, yeah, it's big. So we have to use that 0.1 minus 1.34 times 10 to the minus 3. So if we are going to continue to calculate that, 1.34 exponent minus 3 squared divided by 0.1 minus 1.34 exponent minus 3. So the answer is just 1.8 times 10 to the minus 5. Ka is equal to 1.8 times 10 to the minus 5. So we obtain the Ka and we obtain the H plus concentration. So with these problems, when you are dealing with weak acids, do not forget to write first the equation. And if you are if you are given the percentage ionization data, do not forget this formula and calculate either the H plus or the initial concentration, so that this will guide you in the proper values to plug in this ICA table. So if you are going to get the acid equilibrium constant, you are going to use the data at the equilibrium, since again, this is the acid dissociation constant at equilibrium. Do not get data from initial and change. You have to get the data from the equilibrium of this ICE table. So let's continue in the case of weak bases. Remember that weak bases, they're only partially ionized in aqueous solution, such that dissolved molecules exist in equilibrium with their ions in solution. So the extent of ionization of a weak base is expressed by the equilibrium constant for the ionization reaction. So this is an example of the ionization of a weak base. So take note that if we have an acid dissociation constant for acid, the expression here is base dissociation constant for base. That is just the same, products over reactants. Neglect the water. So the magnitude of Kb indicates the tendency of the hydroxide atom to ionize. The larger the value of Kb, the stronger the base. So there are examples of bases, weak bases in water, and their Kb values at 25 degrees Celsius. So for bases, we also have our percentage ionization, in which that is equal to the concentration of your hydroxide in equilibrium over the initial concentration of your base times 100. Take note that the percentage ionization is directly related to the base dissociation constant. The smaller the Kb value, the lesser the degree of ionization. The lesser the degree of ionization, the weaker the base. So this is an exercise. In a 0.25 molar solution benzylamine, the concentration of OH minus is 2.4 times 10 to the minus 3. What is the percentage ionization and the value of Kb for the aqueous ionization of benzylamine? So let's check next slide. This is the problem. Take note that this is a weak base problem. So we have the initial concentration of our benzylamine given, and next the OH minus concentration. So what we are going to do now is to write first the chemical reaction involved. So first we have a benzylamine, which is a C7H7NH2 plus H2O. So take note that this one is the base, and your water is amphoteric or amphiprotic, so it can act as an acid in the presence of your base. So you have your OH minus concentration, and we have our C7H7NH3 plus. Now, our initial concentration change and equilibrium concentration for this reaction will be obtained via the ICE table. So we have an initial concentration for our benzylamine, which is equal to 0.25. So we have a zero amount here at the initial. Then during change, we have an increasing concentration of our hydroxide, which is equal to 2.4 times 10 to the minus 3. Since the concentration of your hydroxide is just directly proportional to your C7H7 and H3 plus, or the conjugate acid of your base, that is just equal to 2. The concentration in product of that conjugate acid, it is equal to 2.4 times 10 to the minus 3. So in order to get the change, that is negative 2.4 times 10 to the minus 3. So in order to get the equilibrium, that is 0.25 minus 2.4 times 10 to the minus 3. Then we have plus 2.4 times 10 to the minus 3, and we have plus 2.4 times 10 to the minus 3. Now, the first question is, what is the percentage ionization? So in order to get the percentage ionization, you have to remember the formula, in which you have the OH minus concentration in equilibrium over the base concentration at starting point. We have the OH minus concentration, which is equal to 2.4 times 10 to the minus 3 over the base concentration, which is equal to 0.25 molar times 100. So I forgot, we have to place this times 100. Okay. So if we are going to calculate, our answer here is equal to 2.4 exponent minus 3 divided by 0.25 times 100. The answer is 0.96. The ionization constant is equal to 0.96. Now, the next question is, we have to calculate for the Kb. Take note that Kb is equal to products over reactants. Our products is OH minus, and we have this C7H7 and NH3 plus. So over the initial concentration of our benzylamine. So sorry for the initial concentration of our benzylamine, which is C7H7 and H2. So Kb here is equal to Kb here is equal to 2.4 times 10 to the minus 3, which is the concentration of your OH at equilibrium, times 2.4 times 10 to the minus 3, or the concentration of your conjugate acid, over the concentration of your benzylamine, which is 0.25 minus 2.4 times 10 to the minus 3. So, we have to get it. 2.4 exponent minus 3 times 2.4 exponent minus 3 divided by 0.25 minus 2.4 exponent minus 3. The answer of Kb is equal to 2.33 times 10 to the minus 5. So that is your Kb of your benzylamine. Now we have the Kb and we have the ionization constant. So problem solved. Next is calculating Kb from pH. A 0.44 molar solution of a weak base, take note weak base, has a pH of 11.12. So what is the ionization constant Kb of the weak base? So if we have the weak base, which is equal to the B, so we can represent it as HB. We can represent it as HB, that will dissociate into OH minus and, well, starting point HB. Now this is HB, but we can represent it as BOH na lang. BOH. Or B na lang, plus H2O. So this is your base. And this is your acid. So your weak base, it grabs the proton. So it will form HB and form OH minus, right? So if we are going, excuse me. So equilibrium sign, sorry. Let's write it properly. It's just equal to we have here B that reacts with water to form HB at equilibrium plus OH minus. So we have to get the ICA table, initial, change, and equilibrium. For base, we have 0.44 as initial concentration, then 0 pa sila sa initial. Sa change, later we will calculate the change. Take note that we have a pH of 11.12. So take note that pH is plus pOH is equal to 14. So we want to get the OH minus concentration. So we have here the pH, which is equal to 11.12. So in order to get the pOH, that is just 14 minus 11.12. So that is equal to 14 minus 11.12. That is equal to 2.88. So once we have our 2.88 here, take note that our pOH is equal to negative log of OH minus concentration. So from this point, we can get our OH minus concentration, which is equal to the inverse of log of the base 10 to the minus of our POH. So that is equal to 10 to the minus 2.88, which is equal to 1.318 times 10 to the minus 3. So therefore, your OH minus concentration is 1.318 times 10 to the minus 3. So we have to place this as our OH minus concentration, 1.318 times 10 to the minus 3 plus 1.318 times 10 to the minus 3. Then this is minus 1.318 times 10 to the minus 3. So if we are going to get the change, 0.44 minus 1.318 times 10 to the minus 3 plus 1.318 times 10 to the minus 3 plus 1.318 times 10 to the minus 3. So if we are going to get, we already have the OH minus concentration by this process. Now, if we are going to get the Kb, we have to get the equilibrium values of this HB, OH minus, and our base. So that is just 1.318 times 10 to the minus 3 times 1.318 times 10 to the minus 3 over 0.44 minus 1.318 times 10 minus 3. So get the square divided by 0.44 minus 1.318 exponent minus 3. That is just, the answer here is 3.96 times 10 minus 6. So that is the Kb. 1.318 exponent minus 3 squared divided by 0.44 minus 1.318 exponent minus 3. That is 3.96 times 10 to the minus 6. So, easy lang ang pag-calculate sa imuhang Kb expression. The same with Ka, but you are dealing here with OH minus.